Okay. Um, I encountered an anomaly in the light curves made by Watec 910 HX cameras, and if I'm not mistaken, Tony George has encountered the same anomaly. And so I just wanted to discuss that with you. And in addition, I wanted to take just a few diversions. Diversion number one, to understand this presentation, you need to understand that a saturated star has its three-dimensional plot has a pointed peak. An unsaturated star is a pointed peak. A saturated star has a flat top. You notice also that the down at the base of this mountain, it's much wider than it is with the unsaturated star. There's a lot more light in this one. Secondly, the Watec 910 HX camera, when it's in non-integrating mode, it functions very similarly to other video cameras in that it only records one line at a time. And that's in the top half of the screen here. It records every other line. So in NTSC mode, that there are 480 recording lines on the image, and it records lines 1, and then 3, and then 5, and then it goes back again through all the lines and records line 2 and line 4 and line 6. But it's only recording with the half of the area of the CCD chip at any one time. One of the big advantages of the camera is that it has another mode, and it's the integrating mode, and we're going to call it 2x. Now, it actually can record more than 2x. It can record up to something like 256x or something like that, which is about a 2-second recording. But the 2x basically makes it record at 30 frames per second, but it records the whole chip. It records the entire surface area of the chip at every one time. And so it actually is an interlaced view, because it still records line 0 and then line 3 and so on. But when it does that, all the other lines are being recorded. They're recording light. Whereas in the non-integrating mode, they're not even recording light. So this makes the camera about twice as sensitive. And that's what we're talking about. So that's one of the big attractions to this camera. And one of the other attractions is very low noise compared to the other super sensitive cameras we've used. I wanted to point out, this is another diversion, something I discovered when I first started using this camera. I set up a set of equipment where I got a new camera, a new time inserter, which you can tell from the bottom here is a Sprite GPS from Great Britain. And I started using a new analog to digital converter. And I noticed that the star images were double. This is the craziest thing you ever saw. And look, this is double, this is double. Every star image, if you can see this with sufficient resolution on your screen, they're all double, side by side. And in fact, when LiMovie puts out the star graph of the star's light, it shows that double peak like that. So that's something that's on this system. And at first, I thought this was crazy. This must have something to do with the 2x setting in the camera. But I found that if I looked very carefully, I could see when I put another camera in, a non-integrating camera, that I could see it also in the non-integrating camera view. But it's difficult to see with other cameras. And the reason is that you see how dark the background is? This is an actual stellar view here. The camera, the Watec 910HX, has very low noise, a dark background, and other super sensitive video cameras have much more noise and a noisier background, which obscured this particular phenomenon. And I was thinking, gee, are our cameras doing this? I eventually figured out that it's only one of my time inserters, one of my analog to digital converters that does this. The analog to digital converter is the device you put between the time inserter and the computer. It makes it so the computer can read the signal which was sent out of the camera as an analog signal. And I want to just point out that it's not a matter of an interlaced effect. These are deinterlaced frames, and we see it on the field view as well, essentially looking the same. And here's the problem. I used to use this old reliable Pinnacle Dazzle DVD 100. They cost $100 in the old days. I just found out today, I searched online, you can get them for about 70 bucks now. Completely reliable, give really good data. This is the one that's causing the double star images. It's made by AverMedia. It's called the Easy Maker analog to digital converter for video, and it's $20 plus or minus. Now, a lot of our analog to digital converters now are in that $20 range, and the one recommended by IOTA is the StarTech one. I've searched for that one. The USB 3 compatible StarTech device currently is not available on eBay, Amazon, or any of the couple other sites I searched. So it may be unavailable, but I wanted to warn you about this particular one because it gives these altered star images. Nevertheless, I'm going to use for the rest of the presentation images from a video that was made using this, and I just wanted you to see up close just how it can affect the star images. Now, most of the time when you make a video with a 910HX camera at the 2x exposure setting, as we have designated up here in the upper right, you get a nice flat curve like this, just like any other star image. Most of them are fine and don't cause any trouble, but every now and then you get something like this. And this goes up and down and up and down and up and down and up and down. As you can see, this is a really weird effect, this up and down effect. Of course, we have a nice occultation in the middle, but there's an inherent problem with this. You see, whatever is causing this up and down effect is not scintillation. I mean, the scintillation noise is just the width of this line that's going up and down. And the problem with that is that the error in timing is inversely related to the square of the signal to noise ratio. So if you plug this into a program, say Peyote, that analyzes the signal to noise ratio and thereby determines the timing error, it's going to include this as noise. And so you actually get a less accurate timing estimate that is a higher error estimate because of this up or down. And you can also imagine that if you have a low magnitude drop, that this background fluctuation in brightness could obscure a low magnitude drop occultation. So this, although in this particular occultation it didn't make much difference, you can imagine how this would be problematic. Okay, here's another one, and look at that one. And a nice occultation, but up and down, up and down, up and down. And that's the problem. If this is the error range, we get a higher estimate of the, if this is the noise range, we get a higher estimate of the error, when actually the noise range may be only this far, you see. And here's another one. Now, I'll tell you, these three videos that I'm showing, these three light curves, this one, and this one, are all from the same event, okay? I mean, it's not because there was a street light nearby going on and off. Was all on the same night with the Hector event on August 28th, 2019, and with different sized telescopes. Let's see, this one is a 14-inch, this is an 11-inch, and that's an 8-inch. And I might also point out to you is if you get over toward the edge of this, you notice that the up and down pattern becomes blurred. And over here it becomes blurred. Now immediately that suggests to me that it's some effect that the light has upon striking the CCD chip. And the reason is that on the edge of this is a recording from where the star is at one edge of the field of view and it drifts across the field. An occultation occurs and it keeps drifting until it exits the field of view of the camera on the other side. In other words, this telescope did not have a clock drive. It was pre-pointed at the sky, and the occultation star drifted across the field of view at the right time. And at the edges of the field of view, we have aberrations in the optics. We have coma, and also the field of view is not flat. And so we have defocus at the edges of the field of view. And since we find that these up and down effect is less prominent at the edges of the field of view, that makes me think that it's an optical aberration such as defocus and coma, and therefore this up and down effect has something to do with the light actually impacting the CCD and just what that looks like. Now, I'm going to have another diversion here. This is another event. This is a Hansa event, and this was also the 910 HX camera at 2x. This is an 11-inch SCT. On the left side of the field of view, you notice the up and down effect over there, and then it gets all blurred up and goes away. Well, you know, I figured this one out. We have a strange light curve over here, which I mean to explain in this talk. Then we have an apparently random light curve for the rest of the recording. And I want to tell you that there is an occultation hidden right here, okay? This light curve is heavily affected by wind, so that LiMovie's aperture could not follow the star. So I took this recording and I imported it into Registax and manually clicked on the star in every frame, and thereby was able to eliminate the effect of the wind, and I got this recording. And if you look carefully over on the left side, you can still see the up and down effect over here. That's not due to, you know, a failure to track by LiMovie, but we were able to extract a nice occultation from a wind damaged recording. Enough of that diversion. What I want to do is I want to look at this part of this light curve, which shows this up and down effect more closely, and I'm gonna stretch it out. So here it is, and it's obviously you're going to have more LiMovie brightness measure here than you will here, and here than you will here, and so on. But I've just put all the numbers in there so you'll know what frame and so on. And what I did is I looked at each of these selected frames up close and magnified what those star images looked like on the video. And here they are. Now, I want to start at the bottom here and show you that these have narrow, basically 3-line heights. And this is narrow, this is 3 lines, this is 3 lines on the video 480 line scheme. These are most of the lights on 3 lines. Whereas up here, the bright part is 6 lines, 6 lines vertical, 6 lines on the Y scale, you might call it, of the video. So these are twice as wide as these. And one of the reasons I showed you the problem with the analog to digital recorder, converter, analog to digital converter earlier, is to just show you how the video is messed up by this analog to digital converter. Really, this height should be the same as the width of the star, but it's not. Here it is, but here the whole thing's twice as wide. In every case, both the top row and the bottom row, the width of the star is about the same. Furthermore, it's supposed to scan the lines, you know, the 480 lines in such a fashion that in 2x mode, the bright part is 2x high, 2 lines high, and here we see it 3. And this should be, the bright part should be 4 lines high, and here we see it 6. So I just point out that your analog to digital converter can really affect your star images, and if you're ever analyzing anything closely on the basis of star images, you really want to have a good analog to digital converter. I want to just show you something else about this. Whoops, wait a minute. Oh, I wanted to say that the horizontal resolution of this camera is said to be 570 TV lines. Now it has 768 horizontal pixels. The camera has an online, it's a CCD camera, and the camera has an in-house, in-camera conversion of this 768 horizontal lines is converted to, they say, 570 TV horizontal lines. So you see, it's really changed. But the vertical isn't changed in the same extent. They got 494 vertical. Some of those aren't used, and they really do scan them, each line. And so what I'm saying is that this analog to digital converter is really messing up the horizontal aspect. It doesn't have the horizontal resolution that that the camera initially puts out, and so it's you know, in that respect, it's not very good. All right, now what I've done on this slide, this is the same as the last one, except I've put in these green numbers, and I use Y because it's the vertical dimension of the field of view. And you'll notice that from here to here, the vertical dimension changed by 2. Now we're in 2x mode. So here, LiMovie says the aperture is centered on line 306. There's my mouse. And here it's on 304, 302, 300, 298. When it's narrow like this, it's just stepping down 2x, that is 2 lines that are being recorded at the same time. And look, the numbers at the top are intermediate between them, 307, 305, 303, and so on. So as it steps down from one line to the next, from 306 to 305, it records on 2 lines of the 2x in the 2x, where there are actually 240 vertical lines. It goes from 306 and to 305. It's recording on 2 lines, and now it's recording on 1, and now it's recording on 2, and now it's recording on 1, and now it's recording on 2, and so on. And when it's recording on 2 lines, it's brighter. Now that immediately makes you think that there's some saturation here. In other words, if this pixel is saturated, it can't send forth all the light. It can't process all the light that comes to it. But if that the light that's impacting the CCD chip is spread over more pixels, it can handle all the light, and therefore looks brighter. No light is lost. So if a star image is fainter when it's confined to fewer pixels, this suggests that the image is partially saturated when it's confined to fewer pixels, right? The problem is that none of these star images is saturated. These are the actual star images of those pixels you were looking at, of those star images. These are the LiMovie effects. You'll notice that we actually see the double peak in some of these. You can see a trace of it there. You see a bit of it there. But none of these is saturated. None of them has a flat top. And so it's not due to saturation. This is due to spreading the light over more than one line causes a brighter star image, and yet it's not due to saturation. Now, this is the reason why. It's because the response of the camera is not linear. Now, I want to credit Tony George with this graph. I guess Tony measured the data. If it may have been one of his coworkers, Bob Anderson or Gerhard Dangle or someone, I don't know. But the blue line is the actual camera response, and you can see when it gets up here, it levels off. The light response levels off. And Tony drew the red line to show what would be more satisfactory. We'd like a linear response that levels off. Now let me point out that the the CCD output is saturated at 1200 millivolts right here. That's saturation of the CCD output. But the video output in millivolts is different. And right at this point, we've got, this is at 600 millivolts, so it's 50% of the maximum CCD output, and yet 81% of the camera's ability to display brightness is occupied by that first 50% of the CCD output voltage. And this is essentially similar to a gamma value greater than 1. What you might think is that, wouldn't it be nice if it stayed linear, and when we get to this point we just had greater camera response? It looks as though maybe we lost some light in the brighter part of the image, but that's really a misunderstanding of what's going on. What's really going on is this: the saturation point is here, and we'd like it to be linear, but the star image is actually brighter than it would have been otherwise in the lower part of the, well, in the whole spectrum of its brightness. And this is light gained in the image, not light that's lost. It's as though you take this star image here, and you take the 50% level and you raise that up to 80 or 81%. The top half, the saturation level is not changed, so the top half is reduced and the bottom half is increased by the same 60%. So we've actually gone from the Burj Khalifa to the Empire State Building. So nonlinearity of the 910HX light response causes an effect similar to what you would expect from saturation. However, instead of the flat-topped stellar profile seen in a case of saturation, the top of the stellar profile in the case of the 910HX's nonlinearity is just less pointed, and the bottom of the profile is relatively enhanced. All right, now this is another case I have, and I just want to show out some of these effects. Obviously, there's a nice occultation in the center, and we see this up and down effect throughout. And what we have here is that in the center of the image, it's near that 81%. It has a long way to go before it gets done with all that effect. At the periphery of the field of view, because this star is drifting across the field of view, at the periphery, we've got the optical aberrations. And this is a small telescope, 105 mm Maxitov, again, 2x with the Watec 910HX. And we've got the aberrations enhanced because of defocus due to non-flatness of the image plane and due to coma. So even though we see the effect here, it can be enhanced out at the periphery, and other times you see it diminished out at the periphery. And whether it's enhanced or diminished depends on where this baseline level is in this scheme of things. If the baseline level is down here somewhere, it may be diminished when you got it at the periphery, I think. And if it's up here somewhere, it may tolerate more spreading or something like that. I'll leave that up to you to figure out the details. Now, I just wanted to say there are some other effects, some aberrations here in the image, and I can best explain those by saying, welcome to the Southeast US. Those are cloud effects. All right, now, can this effect caused by nonlinearity also be seen in cases of saturation? Well, here's a star that is just a little bit saturated on top, a slightly saturated stellar profile. And here's the pattern with it. You don't see the effect much in the center. You see a little bit of it out at the edges. And that's just because of the way this particular star brightness pattern impacts the CCD chip. And here we have one that's got a little more saturation, and it has some of the effect too, but not very much. This is nothing like what I was showing you with those other images. The saturation seems to diminish the degree to which this effect is evident, not cause it. Here's one, we'll say this has a moderate degree of saturation. This star's got a little comb out to one side or something, some type of optical aberration causing the star image not to be round. And this one, you know, you really have to try to persuade yourself if there's any effect there. I don't really see the up and down effect. I think this is mostly just noise. And so I'm not going to even bother to show you the light curve of the Devil's Tower of saturation. So you get the picture. Questions, answers, comments?
So that's pretty interesting. So in my mind, that's sort of like a dithering effect that's sinusoidal. So as you're drifting over, all these are drift observations. So the star image is slowly moving across rows.
Yeah, every one of these is a drift through event from an unattended station. Even my attended stations, I use the drift technique. That is, I pre-point the star to some star field just in advance in right ascension of the target star, and I just let it drift across my field of view. That's just a real certain way of getting it right, so that I don't touch the telescope during the time when I'm making the important observation. So the drift through technique like that, the pre-pointing technique, is a good way to make an observation. And every one of these, we see it going, it doesn't go exactly along a particular line, a Y line, you know, one of the horizontal lines. It's the rotation of the camera in the receiver of the telescope is never perfectly right to left in right ascension. There's always a little drift from one Y line to another Y line, and that influences the camera's perception of the star's brightness. That's what I'm getting at.
Okay.
And I did want to point out how you can degrade your star image by having a bad analog to digital converter. So that's plays into this a little bit as you look at the magnified star images.
So you might,
Roger, I'd like to just, I won't counter what you're saying, but everything you presented is counter to what I see when I look at literally dozens, if not hundreds, of other observations that I get from around the United States. And everything that I've seen in your graphics are unique to you and not to the Watt 910HX. I use 2X all the time. I don't see what you're seeing. It may be your capture device. It may be your power supply. But whatever you're seeing is unique to you, and it's not a function of that of the response curve that you showed. The response curve that you showed is actually one that we got from Watec. Bob Anderson did some testing with his ArtStar device, and we saw a knee in the response curve. And then when we asked Watec about it, they came back and said, yes, there is a knee in the response curve, but we could give you a different response curve, which they highlighted in that red graph. And we said, no, as long as we know there's a knee there, we're just trying to confirm it. We don't want you to change the response curve. Also, they were going to charge us extra to do that. So that response curve, it just can't cause the sinusoidal effects that you're seeing. Also, the change in the size of your stars from 2 lines to 4 lines or 3 to 6 or whatever has got to be caused by maybe your A to D capture device is jamming your fields, you know, missing a field or jamming a field or something in its capture. But I appreciate all the effort you've done here, but I don't want anybody else out there to think that there's anything wrong with the Watec camera. There isn't. It's a good camera.
Let me just say that I showed 3 images, 3 light curves from the same event with 3 different telescopes, 3 different computers, and they all had different video time inserters. One of them had the Sprite GPS, one of them had the Kiwi, and one of them was using the IOTA VTI. They all gave the same response. And they also had 3 different analog to digital converters. Only one of them actually had the distortions, the analog to digital converter that displayed the distortions that I showed. And I used that one as the example because I just wanted to sensitize people to the idea that their images, star images, could be affected by their analog to digital converter, could be affected adversely. But all 3 of those from the same event showed the same problem. Not only that, I showed a couple others from other events with other telescopes that showed the same problem. Furthermore, when you say that the positive gamma function greater than 1, which is equivalent to a gamma greater than 1, can't cause this, that's not true, Tony. It can, and I explained that it can. And I think that if you review the presentation again, you'll figure out that it can cause this, and it does. So,
Yeah,
you know, when I showed the Y lines, I pointed out the specific lines and how it was changing from line to line, and that affected the brightness. Now, Tony, if it's changing from line to line and that changes the brightness, which is exactly what I showed, and the brighter ones have twice as many pixels exposed as the narrow ones, that tells you, Tony, that's the proof. And I'll just leave it to you to refute it. But just saying that it can't happen, I'm sorry, I don't consider that refutation.
No, I'm just going to respectfully disagree that you're conflating some other problem with the answer that you're giving is all I'm saying. So I'd be looking at power supplies. Something else is going on. I know that Paul Maley reminded me that he had changed to a different power source, and we saw that kind of a response in one of his recordings, and then when he flipped to a new power source, that response went away. So well,
I respect that, but I would point out again that what we need to do is explain how, when it goes from 1 line to 2 lines, as you saw with the magnified star images, that its brightness changes in harmony with that change. That's the key. That's the evidence in support of what I'm saying.
Right. And, we saw that a long time ago when we were using the PC164CEX2 camera. We would see that it had some sort of an enhancement thing built into the chip where as the star moved downward in the different lines, that sometimes 2 lines would light up, other times 3 lines, and there were extra pixels involved, and we saw that sinusoidal effect, and it was always repeatable, was always with that specific camera. But I'm getting videos from other people that have drift scans, and we're not seeing that. So that's why I'm thinking something is unique to what you're doing there.
Roger, have you done any captures with a guided scope at all? Because I'm wondering, if these are all drift scans, we have theory here that I think that you've strongly presented that it looks like it's drifting across multiple lines, but there's also talk of maybe, some kind of 60 hertz clock thing, which, might not be because you're using batteries. But I'm wondering if it's physically the image moving across the lines, we might be able to eliminate that variable.
You can actually see it on the videos. You can
Right.
see how the star image, if you're well focused, the star image actually changes from 1 line to 2 lines as you just watch it drift horizontally across the field of view. And I'm saying that that does correspond with its apparent brightness. Now, I do occasionally some occultation observations with a clock drive running, yes. And I don't do many of those just because it's actually, I consider it less secure. The simple thing is to stand away from the telescope.
Right.
And that's why I
But-
use the drift through
But
technique.
my question is, do you see this sinusoidal pattern on any of the on any of the guided shots?
You
Because
will
that
if
might,
there's declination drift.
okay,
Yeah,
but
I
if
mean,
if
it depends
you're
on how
like,
the camera. Yeah, it
but
depends on whether it's drifting across the y-axis of the,
right, but
if there's
do you see it less with like if you had a pretty good alignment so that you're an equatorial mount, so that there's little or no drift during a 2 or 3 minute capture, do you then see the sinusoidal effect much less?
No, you don't see it at all.
Okay, so
if it's not drifting.
Okay, so that my point there is that I think, yeah, then that is a point in support of it seeming to be a physical effect of the light hitting different lines, as opposed to maybe an electronics artifact later downstream of the A to D getting a beat phase in and out of some other clock and deciding to,
Right.
I'm going to pick odd lines now I'm going to make even lines, so that
I only use the clock drive when it's a very faint star that requires a lot of integration and has a high uncertainty in timing, so that it's the event plus the uncertainties of timing won't fit upon the drift field of view. So then I turn on the clock drive. That requires me to carry an extra battery or something,
Right.
so I don't often do that. But I've done it within the last few years for Pluto, for Triton, and for Quoar just a few weeks ago.
Right.
And I can just tell you that there's no such fluctuating change in the light when it's in clock drive mode. Okay.
Oh,
I mean,
okay,
my
good.
observations of
La arena, Mónica, la arena.
Okay, so that to me is
La
a
arena
strong point in favor of
puede
being at the upstream optical end of light dithering across CCD pixels, as opposed to a downstream end of A to D conversion, because then regardless of the optics hitting it, you should see the same. If it was an electronics
Right.
thing, I would expect that drift to be time based all the time, regardless of whether you were doing a drift scan or a tracked one.
Right. I understand. Yeah. No effect when I'm
in clock drive. Okay.
in clock drive.
And these aren't like the CCDs used here. These aren't like some bare matrix color CCDs that then they're just sending out a black and white signal from. So we have like some bare matrix dithering effect going on, right? This is just a true monochrome CMOS.
That's correct. Yeah. It's a real nice camera.
Hmm.
By the way, you won't see the effect if the camera's not at a really fairly parallel to the right ascension direction, so that the star drifts along in the right ascension axis. Because if it crosses the Y lines very frequently, it'll just look like any other noise.
Right, because this has to stretch out over many frames so that
Right.
yeah.
I mean, typically it'd be 5 seconds or 10 seconds or something, and then then you'll see it. Okay, well, I'm done, and I want to mute now. And is Conrad with us? Conrad, go.